Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel, and now I'm once again here as I promised with the second fundamental theorem of calculus. And you can see here this is a previous videos preview related to the first fundamental theorem of calculus that we exhaustively try to understand along with the relevant example in the light of Riemann sum, you can see. And in order to view this entire theorem, you can visit the link of the first fundamental theorem of calculus present in the description box. And in the light of this theorem, we understood I must say, in the light of this example, we understood the theorem entirely that illustrates this whole thing. That if there is a function f, which is continuous in a closed interval ab, and there is any value x belonging to this interval, then there is going to exist a function for all such values of x. There is going to exist a function capital F, which is expressed as the integral of this small f function. All right, so if a small f function is continuous, then it is definitely going to be integrable in the corresponding closed interval. So once when we take the antiderivative of this capital F of x, we are going to get this small f of x function back. That's what your first fundamental theorem asserted. Now, in the light of this first fundamental theorem, or we say by taking the support of this fundamental theorem, the first one, we are going to understand in today's video the second fundamental theorem of calculus. All right, so you can see here, this is the second fundamental theorem of calculus, which was so presented by Isaac Barrow, who belonged to this century, the 17th century, and he was the mentor of Newton in the Cambridge University. So he presented a second fundamental theorem of calculus that we are going to prove here. And what this theorem asserted over here is that if there is a function f which is continuous on the closed interval ab, then there is going to exist another function which is represented by capital F, which is the integral function of small f. So once when we take the derivative of this function, we are going to get this function back as it is said over here for all values of x which belong to this closed interval ab. So if this condition is satisfied, because this is something that is taken from the first fundamental theorem, so that's why I found it necessary to give a preview of the previous link. That's what I did. So if this condition is satisfied, then you can say that the integral of this small f of x function from point x equals to a to x equals to b, the area under the curve can be expressed by taking f of b minus f of a. So how this thing has been evaluated, how this thing has been derived, we are going to prove this, and then we'll try to understand this equation, this calculus equation, geometrically, so that we could get a much better picture in our mind how this theorem, what exactly this theorem is telling us. Okay, so let's begin and try to understand the proof of this theorem. So here you go. Okay, now I have just assumed here an arbitrary function f of x, and I just tried to plot this f of x function on a piece of graph, and I just obtain a curve representing this function f of x over here in this form. And on the x-axis, I just assigned here two values of x, which are a and b, and I just maintained here a segment of this curve which belong to this interval a to b, and then I divided this entire distance between a to b into small segments of equal width, of same width. Okay, and I just call these segments are the partitions from point A to point B on the x-axis. All right, so what exactly the second fundamental theorem is telling us, it is going to help us to understand how we calculate the area under the curve y is equals to f of x bounded by these two lines, x equals to a and x equals to b, and which is right above, this region is right above the x-axis. So it is actually restricted by these two lines, by this curve and by this x-axis. So we are going to find out the area of this bounded region. So what is is there any algebraic shortcut formula like that could help us out in getting the area and could save our time? So second fundamental theorem is actually dealing this entire stuff. Okay, so what we did over here, I just divided my the distance from point A and point B on the x-axis into infinite number of segments of same width, and I just call them the width from A to this point is, I just call this point as x1, this point is x2, this is your x3, and it's going on up to xn, okay, and so on. And the width between each two points or each two partition is expressed as del x, okay, and this is extremely small approaching to 0, and this thing gets possible once when you increase the number of partitions or the number of segments. So this thing tells us that once when number of partition or the number of segments expressed by n, once when it approaches to infinity, means if you're increasing the number of segments extremely larger, then the width of each segment will reduce as much as possible, and it will approach to 0. That's what exactly it means. Okay, so we are now going to do what? We just say that let this entire distance from point A to point B, just call it P. Okay, we just call it P, and it contains all these distances as their elements, as the element of this set P, which are actually, this is the set of the partitions that I have just tried to maintain over here. So I just call the set of the partition as P, or you can say like that. So it is going from x1, x2, x3, and so on up to xn. All right, and they are extremely larger numbers. The number of n is extremely larger. It is approaching to infinity. You cannot clearly define the exact number of n. Okay, so assume that they are extremely large in quantity. All right, so that's it. And as far as your width of del the value of del x, or the value of the width of each partition is concerned, it is constant. What exactly the value of del x is? So you see, this is the entire distance that we are dealing with from point A to point B. So how you calculate this distance? You see that the distance from origin to point B is exactly from here to here. If you just try to understand, it is the length B, and the distance from here to here is length A. Okay, so once when you subtract length A from this length B, you are going to get this much distance back. Okay, so this is what the required distance is that we are dealing here in this theorem. Okay, so what you do, once when you divide the given distance with the number of partitions, you are going to get the value of del x, or the value of the width of the partition, of each partition. All right, so your del x can be defined as b minus a upon n. All right, so this is it up till now. Now, after understanding the value of your del x, we are going to, or we'll try to inspect the function capital F, which is the integral function of your small f function. So you see, according to the we have studied quite deeply, or we try to understand quite exhaustively, the LAGRANGE's mean value theorem in one of my previous video. You can find the link in the description box. So over there we have studied all the hypothesis points of your function that satisfies the mean value theorem. So f function over here that we are looking over in this theorem, it also satisfies the hypothesis points, or the hypothesis of your mean value theorem, for all intervals, all the sub-intervals that we are having over here in this partition. So that is, it is continuous in all these sub-intervals. This function f is continuous in all these sub-intervals, and also it is differentiable on the open subintervals as well. Okay, so you see, once it is satisfying the mean value theorem, so it means it is also going to satisfy the remaining part of the mean value theorem. So that's what we are going to discuss, and that's a point that is going to help us out in further taking this theorem onwards. So you see, if it is satisfying your mean value theorem on each of the closed subintervals, we are going to assign, like, we are picking subintervals like this from x2 to x1 or x3 to x1. That's what we have assigned. From partition to partition, we just maintain a closed intervals, or, and it's going on. One thing I just messed up here. I should write small value first and the larger value afterwards. Small value first and the larger value afterwards, and so on. You keep on going, small value first and the larger value afterwards. So that's all. So you see, these are the closed subintervals that we have picked from this distance a to b. Okay, and your f is satisfying the hypothesis of your mean value theorem, that is, your function capital F is continuous in all these intervals and differentiable on the open intervals. The corresponding open intervals as well. It is differentiable. Your mean value theorem and the first fundamental theorem of calculus has asserted this thing quite well. Okay, that's it. So you see, if f is continuous in a closed interval, differentiable in an open interval, then there is going to exist at least one point. We are picking up this generalized interval, okay? So there is going to exist at least one point. We can use any notation in the subinterval we want. How about if I just take as my xk star? All right. So there exists one point at least in this open interval okay, such that well, this is the remaining part of your mean value theorem, because if the function is satisfying the hypothesis points, and it is going to satisfy that the ratio, sorry, my K is quite horrible, and the ratio of these two values, rise over run, or the slope of this thing, is equal to the derivative of this function evaluated at this point. That's what exactly it means. Okay, so this is it. Now we are going to take the reference of our first fundamental theorem, and over there we studied that according to your first fundamental, I'm not writing theory, I'm simply going on to the points of the theorem. So your first fundamental theorem asserted that if your small f is continuous on the closed interval AB, and f is a function that satisfies this condition throughout the interval, then this equation is going to be satisfied. So you see the first fundamental theorem over here. I would like to put down the theorem over here once again. So you see the first fundamental theorem explains that f dash x, or the derivative of this integral function of f, gives you the original function is small f of x back. So it means I can replace this f dash x k star by small f of xk star, right? And this is your width of the partition. It can be replaced by your del x. So let us shift this denominator over here at the right hand side. So it is going to give me I'm going to make here a logical shift, and it's an algebraic shift. So this is your del x, okay? So I'm going to replace this stuff by f of x k star according to your first fundamental theorem. The derivative of the integral function of this function gives you a small f of x back. That's what I've taken. I've just taken the reference of that, and this is your del x. All right. Okay, now this is a very important step that we have just extracted, and it's going to help us out in getting this equation, all right, in a systematic way. Now, as you see, I can interpret my the entire partition or entire subintervals in a way that is, if I just take from the point of beginning, from the beginning, if I just take that, I just started making my partitions in this distance a to b from x0, x1, x2 up to xn. So I'm just talking about my very first partition, all right? So it is from xa to x1. This is the very first partition, all right? I'm talking about this subinterval first of all, okay? So it becomes f of x1 minus f of xa, and also I can replace this xa as my a only. Okay, so here my xk is behaving as my x1, xk minus 1, which is the lower limit of your closed interval, is behaving as your a. So I can write it like this. Okay, and it is equal to here, it is xk star. So I'm going to follow here the value in the subscript which is present over here. So over here I'm having 1, so I'm going to write here x1 star. Okay, this is said to be my equation number 1, for example. In the same way, now I'm going to move towards my second subinterval, which is from x2 to x1. This is the partition that I'm talking about. So over here the story is going to be repeated exactly in the same way. So it is going from x2 to x1, and it is expressed as f of x2, small f of x2 star. This is my equation number 2. Let's move on and write one more. Now the third subinterval, it is this, from x3 to x2. This closed subinterval I'm talking about, I'm going to repeat this entire step for this third subinterval, starting from the upper limit to the lower limit. And it is giving me, it is equivalent to this thing. Okay, you keep on moving till you achieve the last subinterval starting from xn to b. All right, this is it. It is expressed as f of b, the upper limit of the interval, to xn. All right, and this is it up to xb star. And this is your nth equation. It's said to be your nth equation. This is your nth equation. So that's it. If you just write a second last equation of this set of equations, it is going to help us out in while performing the addition process of all these equations. So if we just move to the second last or one step back in writing the equations over here, so it is going to be the second last subinterval is actually from xn minus 1 to xn. This thing is your xn minus 1. So this interval I'm talking about is said to be the second last sub-interval starting from xn minus 1 to xn. So this one is the xn is the upper limit and xn minus 1 is the lower limit. So we are going to repeat this activity over here. And it is giving us like this. This is your n minus 1th equation. All right, now we are going to add up all these equations from 1 to n. All these n equations we are going to add up. Let's see what we are going to have. So I need a new page. How about if I just carry on? I'm still having some little space left, so just give me a break. Let me adjust the page. Okay, now once when I just try to add up all these values, how about once when I add up all these, and my bad, I just forgot to write del x everywhere. So del x is everywhere here, I'm sorry. While going with the flow, I forgot to write. So my apologies. So it is all containing del x along with it. So now you just add up all these things. So adding all equations. Now what is going to have, no need to write all these, this plus this plus this plus this. If I just write it in a way, it's summation. I is going from 1 to n, or k is going from 1 to n, like that. Del x. Okay, so it means that it is talking about this. F of x1 star del x plus f x2 star del x. That's what it means, and it is we'll keep on moving till we got f of xb, or we can also write simply b over here instead of writing f of b. It's your choice. So it's just a matter of representations, nothing else. So this is it. Now we are going to replace all these values by the corresponding capital F of function difference. All right, so now I really need a next page. Okay, now at the place of your f of x1 star del x, I'm going to write this thing. Plus, at the place of this stuff, I'm going to write down f of x2 minus f of x1. Okay, at the place of this, I'm going to write f of x3 minus f of x2, and I'll keep on moving. I'll keep on moving till I'm approached to the n minus 1th equation. I'd achieve over here. I just reached over here, and it is going to be written like this. And the final one, this stuff is going to be replaced by this. Okay, so you can see that f of 1 positive can be cancelled out by this f of 1. This plus f of x2 is going to be cancelled out by negative f of x2, and similarly, all these values are going to be cancelled out. This positive f of xn is going to be cancelled with the negative f of xn, so on. All these values will be cancelled out, and because we haven't written all of them because we do not know the exact value of n. So it's simply that we are going to generalize, and what is exactly left is simply f of b and f of a over here. All right, so this thing is equal to this. Now if I just try to maintain here a continuity, and I just say that how about if your partitions are extremely large in quantity, they're extremely higher in number, so this is going to reduce the width of each interval. It will approach to 0, as I have written earlier, that if your number of partition is approaching to infinity, then the value or the norm or the distance of the interval, each subinterval, will approach to 0. So now once there is a limit over here, so we are going to replace this Greek summation with our calculus elongated s, okay, while moving from point A, x equals to A, to x equals to B. So we are going to replace this summation with our elongated s sum, starting from point A to point B, f of x, okay. So no need to write xk star and all that, because now the partitions are all covered in this elongated s, so no need to write anything in the subscript or in the superscript like that. And del x is going to be replaced by our differential x, because if your del x is extremely small, approaches to 0, it is going to be written in this way. So that's what it is said. So this is b, all right, and it is equals to your f of b minus f of a. That's what your second fundamental theorem says. And you can now, I hope you have now understood that second fundamental theorem is actually supported or backed up by your Riemann sum, by your Lagrange's mean value theorem, and by your first fundamental theorem. All right, so all these three theorems are helping you out a lot in understanding the second, or in evaluating or proving the second fundamental theorem. And you can see here that second fundamental theorem is helping you to understand that definite integral, the limit, the integral which is defined by some number values in the upper and lower limits over here. So this is it, and you can see that the area under the curve, let me give you a reference, at area under the curve f of x bounded by x equals to a and x equals to b lines, and by the x-axis, this area is equal, whatever the numerical value you're going to get, this numerical value will be equivalent to the difference of the y coordinates of this function, integral function of your f. So how about if you just try to understand this thing algebraically? If I say that I'm having f of x, this is my f of x, small f of x equals to 3x squared, all right, and your capital F of x, which is actually the integral function of your this thing, okay, it is 3x cubed upon 3. I'm doing quite directly, so it is your x cubed plus some constant. So this is it. This is your f of x. So you see here, and if I just assign my limits, then there is no need of putting constants. Okay, so then I'm going to write down, this is tough, as a to b. All right, so now if I just try to plot this small f of x graph and this capital F of x graph, x cubed, then we'll try to understand how this thing is equivalent to this. Okay, hang on for a second. Okay, so I should assign here some value of a and b, some number values to a and b. So I just say that let it be -2 to 2. Okay, so f of x is d of x, and here my f of x is 3x squared, that we have done this thing already here. So on solving, I'm having x cubed from -2 to 2. Okay, so this is it. So actually what exactly this integral is telling us, this definite integral is telling us what? It is explaining us the area bounded by this curve by these two values, x equals to -2 and x equals to 2, and above the x-axis. So the area which is bounded by this curve, f of x equals to 3x squared, bounded by these dotted lines, x equals to 2 and x equals to -2, and by the x-axis, so the area which is lying above is expressed here by the shaded region. So this area value, whatever it comes, will be exactly equal to the difference of the ordinates, or the difference of the y coordinates of this function graph. So here your f of x is x cubed. So whatever your f of 2 comes, it is giving us this value. And the f of minus 2, which is f of a, and this is f of b, you can take it like that. So f of 2 is explaining us value 8, and f of minus 2 is explaining us value negative 8. Okay, so the difference of these two values gives us the area bounded by this curve and these lines. It will be equivalent to that thing. So it won't be wrong if I say that we have the second fundamental theorem of calculus has related a two-dimensional quantity with a unidimensional thing. It won't be wrong if we say like that. So now let us calculate that if this thing is equal to, this is tough. So let us now apply this formula over here. So our f of x is this function x cubed. So this is your f of b minus f of a. So it is equal to your 8 minus 8. So it is equals to your 16 square units. Why I'm writing square units? Because it is explaining you the area under the given curve. Under the given curve f of x, the lines x equals to a and x equals to b, which are actually minus 2 and 2, and x-axis. Okay, so that's it. So that's all for today, and I hope you have understood this video might have helped you to understand the concept. If yes, then please subscribe and like my video and share it with your friends, and put your feedback on the comment box. Take good care of yourself. I'll see you in the future with more helpful videos. Allah Hafiz.